Hi, my name is Elen Sargsyan and I am a PhD student in Ellipse team at IRIT in France. Today I will present to you a 3D printed interactive multi-story model for people with visual impairments that we designed in collaboration with two orientation and mobility instructors. According to the World Health Organization, there are 2.2 billion people with visual impairments in the world. The independent mobility and the prevention of social isolation is crucial for autonomy and quality of life of people with visual impairments and rely on orientation and mobility trainings. Orientation and mobility training relies on orientation and mobility instructors, and the goal of OMIs is to teach to people with visual impairments to navigate in autonomy, security, and to create a cognitive map of the environment. OMIs rely on existing tools, such as tactile maps or magnet boards, during their classroom or on-site sessions. These tools have several limitations, such as basic magnet shapes or limited amount of information, also the continuous back and forth movements for the legend. Another limitation is the understanding of multi-story buildings, and most particularly the correspondences between the floors. The task is complicated because several floors of the same building are displayed side by side. All these constraints are limitations for the OMIs and affect the quality of orientation and mobility training. It has been shown that do-it-yourself DIY methods, and more particularly 3D printings, can empower special education teachers. Indeed, it has been shown that 3D is better for understanding of elements that are difficult to represent in 2D. Also, 3D is a good technique to represent details. In addition, it has been shown that 3D interactive model is a useful tool for people with visual impairments. Moreover, it has been shown that interactivity improves spatial understanding and memorization, usability of geographical maps, performance during a learning task, and interactivity can facilitate cognitive processes, including spatial cognition. To sum up, in this research work, we have tried to overcome one of the challenges faced by orientation and mobility instructors and their students, which is the teaching of complex multi-story buildings. Considering the previous works, we have set the following research questions. I will now explain you how we answered each of our research questions. Our first research question was, what are the OMI's needs to teach complex settings with multiple floors? First of all, we conducted a co-design with two orientation and mobility instructors. All the co-design process steps were iterative, and one of the authors, a legally blind HCI researcher, was included in all steps of the design. We conducted two focus groups in order to identify the needs of OMIs, and two brainstorming sessions to generate design ideas. We organized all the design ideas into a set of design recommendations. OMIs needed a 3D printed model with overlaid floors where all the essential information related to navigation should remain. The model should have the possibility of adapted level of information and isolated exploration of different parts. The model should be interactive with pen-friend labels. Our second research question was, can we create a low-cost, high-fidelity interactive model that meets the OMI's needs? We started to design the first prototypes, to print them and to test them with our blind end user and orientation and mobility instructors. Based on their feedbacks, we made a lot of design improvements. One of them is the color contrast that you can see on the slide. This is one part of the model with two possible configurations: no spacing between the floors and 10 centimeters between the items, which allows a freer exploration. Here you can see the final 3D printed model. We addressed our third research question, which was, will the resulting interactive 3D model be more efficient and satisfying for learning spatial knowledge about a multi-story building than the regular interactive tactile maps? We conducted a comparative study between our model and 2D tactile maps corresponding to the same building. All the interactive labels were same on both devices. We recruited 6 pairs of participants, 4 different OMIs, one of them participated to the co-design process, and 6 participants with visual impairments and different spatial skills. All the participants had exploration sessions with both devices. The order was counterbalanced between the participants. All the participants had one last on-site session. We conducted semi-structured interviews based on MICU survey in order to assess the UX dimensions for each device. Here we can see that the results were better for the 3D model. After the 2 exploration sessions, participants were asked about their preferences. All participants preferred the 3D model because it was considered as more efficient, useful, pleasant, and playful. Participants claimed to better recognize the items, and even though the on-site session took place after the exploration of the 2D tactile maps and 3D model, orientation and mobility instructors and participants claimed that the 3D model helped to better understand the correspondences between the floors and have a complete understanding and representation of the environment. According to the OMIs, the 3D model is a good teaching tool for multi-story buildings. It provides the participants with autonomy and them with comfort. However, because of its size, it can't be carried to on-site navigation and is complementary with 2D tactile maps. We addressed our last research question based on recommendations and print files. How easily can we replicate in another setting? We created a new model and the making time was reduced by 3 because we used the existing files from the first model. We tested this model with 4 children, and according to their OMI, the 3D model is less abstract, and even though the kids are not tactile readers, they could understand the building organization, and it was useful for survey and route understanding. But despite the benefits, these tools are not available for the OMIs. To conclude, here we presented a low-cost 3D printed models, and we showed that they can significantly empower the OMI and improve the quality of teaching of orientation and mobility. We are conscious that not all of OMIs have the required time and skills to create this kind of devices, but some of them are already included in a maker community, or they know Fab Labs, or they ask the help of their colleagues, such as tactile document makers, who are already making tactile maps. In conclusion, we are confident that the numerous online databases, tools and methods, but also the existence of numerous local Fab Labs can support the spreading of such tools in the spatial education community. Thank you, and feel free if you have questions.